We're deriving a Kalman filter using a pretty brute force and probably non-elegant way to do it. But let's continue with that. We had already basically done the Lou part of blue, the linear, unbiased, recursive filter. And here's where everything stood. We had a way to propagate our estimate from time step k to time step k plus 1. And then we had a way to update our estimates once we process the measurement at time k. So we go to k plus 1, and then at measurement k plus 1, we can process that measurement. And we just kind of keep doing this. I'll show this in a minute. So all that was left really was finding the k that optimized things, which really meant minimizing the mean square error of our estimate, which meant minimize the trace of this p. And I already went through how that works. That why minimizing the trace means you're finding the best estimate. You're minimizing the sum of the squared errors. And we did that because we have these matrix tools for traces. We can take the derivative of a trace with respect to a vector. And I'm going to zip through this because it's tedious and you probably don't care about it, but I'll at least outline it. So all up here is all the little formulas we would need to do this. Here's the P that we're trying to minimize the trace of. Here's where we were left off from previous videos and previous charts. If you multiply this out so you get it kind of term by term, you get this thing. Then we're going to take the trace of this mess and simplify some of that, and we get this down here. And these little subscripts here are trying to show you how to use these formulas and apply it to these particular variables. So here's where we were, and we want to use these formulas now. We want to take some derivatives. Because remember when I talked about optimal estimation in the previous module, module 6, we said how to find the minimum of something. And we had necessary and sufficient conditions to do that. When it involved matrices, you would take the derivative of a scalar with respect to a vector. And the necessary condition was that that derivative was 0. And we had second order conditions involving the Hessian or the second derivative. But this first order condition, so we're going to take the derivative of the trace as a scalar with respect to this vector k. And we get this and we want it to be 0. That's what the first order condition is. The derivative equals 0. And when you do that, you get a formula for what the gain is. Now we have our optimal gain k. And I won't go into second order conditions. They basically amount to, was your original system even observable? If you go back to the state space model, there's no guarantee that that's an observable system. That you can reconstruct the state vector x from a bunch of measurements z. But we're just assuming we can do that now. If your system is not observable, you can't do a Kalman filter. And I know I'm just stepping through a bunch of stuff quickly to save you the tedium. Here was that formula for the P after we update it with the measurement. This first line applied for any gain k. But if we use the k we just found, you go through all this tedium, there's a much simpler formula for updating the covariance. You go from this line to just this line. And we'll talk about that. There's some engineers who prefer to use this regardless, because little errors might creep in. Um, we're gonna assume we can use this. So we now have everything. Here's the way we propagate from time step k to time step k plus 1. And here's how we calculate the gain and update the state and the covariance matrix once we process the measurement at a time k. Here's what's going on. We have measurements, these dots. We have pre-measurement estimates, these squares. And then we have post-measurement estimates, these little circles. If I connect all the circles, I have this solid line. Let's look at right here, for example. Going from here to there. This little circle was the post-measurement estimate. We use that to propagate up to time k. This would be time k plus 1. This would be the x of k minus 1 propagated up to time k. And we get this square up here. That's the pre-measurement estimate. And then once we're there, we make a measurement, this little dot here. And then our gain says how much to balance those two. Right, how much do we want to correct our estimate by weighting between these two. What we measure and our predicted state. And we'll say it's this little circle here. And then at that time, we propagate up to the next times k plus 1. We get to this square, which is a prediction. Get another measurement down here. The gain balances the two, and we have an updated state, post-measurement k plus 1. That's how this, it's kind of hard to visualize all this time stepping as I went through this rather laborious derivation. But this is the gist of a Kalman filter. This chart explains the Kalman filter. These equations are done by computers. X can be very large, the phi can be very large. You let computers do this stuff for bigger problems, for more realistic problems. I'll continue this. What this picture, like from the previous chart, was for the state. The variance might look something more like this. Between measurements, it's going to grow. We're not getting any measurements, so it's only going to grow because of that, because there's process noise. But then once we get a measurement, boom, we bring it down. We bring down our error, the covariance of our error. And hopefully it just keeps going down, and it might reach a steady state, depending. Well, if all our matrices are constants, it should reach a steady state unless things get worse and worse. But this is kind of what goes on with the variance. This was the state, and this is the variance. So that is the Kalman filter. If you want it in one chart, it's this chart. Kind of a painful derivation. Some people don't care about the derivation. And like I said, this is probably not the most elegant derivation. It's not the way Kalman did it in his original paper. And it's usually this is taught in grad school, and it's not the way they teach it in grad school either. This is kind of a brute force way that undergrads could maybe understand it if you take it on faith. All this math about traces and vector calculus. Anyway, that's it. We'll talk about doing some problems and how to manipulate things using this Kalman filter.